Swayam Prabha. Digital India. Educated India.
So, very good afternoon, and today we will look at the different velocity profiles. The last class we had quickly derived the velocity profile in the laminar sublayer, in the log layer. We will summarize that and then quickly move on to the heat transfer. So far we have not really focused on heat transfer per se. This is a very generic discussion on turbulence, okay, which you will find in any basic book. We will now slowly transition to what happens when you want to consider turbulent heat transfer, particular focus on that, and how different it is going to be from modeling the turbulent flow field. Okay. So, in fact, we will use some kind of analogies the same way that we did in the laminar flow, and as I told you, the most rigorous way of looking at turbulence is to therefore solve the Rance equations. Okay. We have the Rance equations for the momentum, where you have the turbulent viscosity, and this has to be solved either by a very simple mixing length approach, provided you have a boundary layer which is always attached. Okay. This is the Prandtl's idea, hypothesis of how the turbulence cascade happens, and then you can solve the energy equation with introduction of a turbulent Prandtl number. So, once you have the turbulent viscosity, you can extract the turbulent thermal diffusivity from this and therefore use that to the solution of the energy equation. So, this has to be done numerically, right, but if you want to bypass the solution to these Rance equations, the only other option in fact which works reasonably well for basic flows such as the flow through ducts and then boundary layer flow. So, we will use some kind of analogies which we will look at in the next couple of classes. Okay. So, today just let me once again summarize the nature of profiles that you find in the within the boundary layer of a turbulent flow. So, usually these are derived either for a simple case like a flow past a flat plate, where you have the turbulent boundary layer and you have a sublayer, okay, or a simple fully developed turbulent fully developed flow through a duct. Okay. So, where you talk about the boundary layers merging and then you also have a growth of a small viscous sublayer. The turbulent boundary layers merge, but there is a small viscous sublayer which is actually still growing in the case of a turbulent fully developed internal flows. So, in these cases you classify this as a laminar sublayer and this is your fully turbulent boundary layer. Okay. So, we have therefore, from the expression for the total shear stress, that is tau is equal to tau wall, which is equal to, we had mu plus tau wall by rho we can use, and then say this is your kinematic laminar kinematic plus turbulent kinematic viscosities times du by dy. So, from this we arrived at the expression in terms of the non-dimensional velocity profile and the non-dimensional y coordinate, which is y plus, we had 1 plus nu t by nu, which is equal to 1. So, we had just manipulated this equation so that we can cast it in non-dimensional u plus and y plus, where your non-dimensional y plus is equal to the dimensional coordinate into u tau by nu. This is your frictional velocity, which is square root of wall shear stress by rho. So, these are your turbulent parameters. There is nothing very logical why we should use a friction velocity here, but it is supposed to scale well for different kinds of Reynolds numbers if you use y plus defined in terms of friction velocity. Okay. And similarly with respect to u plus, we have used u by u tau. So from this, so we have differentiated into a laminar sublayer. So for the laminar sublayer case, your nu t by nu will be very small compared to 1, and therefore we get a linear variation in the velocity profile. So therefore here we got the profile which was u plus is equal to y plus, whereas in the turbulent boundary layer, if you neglect the laminar sublayer and assume only a turbulent boundary layer which is present throughout, we got the fact that nu t by nu is much greater than 1, and therefore we substituted for nu t from the Prandtl's mixing length model. Okay. In the Prandtl's mixing length model, the turbulent viscosity was assumed to be a function of what? The length scale, which is the mixing length, and the velocity scale. So essentially you have therefore Lm square into du by dy, and a kind of a very empirical, crude empirical guess for the mixing length will be the von Karman constant times the actual distance from the vertical distance from the wall y. Okay. So if you consider the effect of laminar sublayer, there will be a damping function. If you consider only a purely turbulent boundary layer, then you do not have that. So therefore we just substitute for this into this, and when we perform the integration, we come out with 1 by k ln of y plus a constant. So this is the nature of the so this should be, yeah, absorbed, correct, you are right. Okay. So the Prandtl, so this is what was originally conceived by Prandtl himself. So this linear layer and the log layer were derived by Prandtl using his mixing length model, and the constant here, this is called the von Karman constant. Von Karman is actually a student of Prandtl. So this is given as 0.41, and this constant C, do you remember what it is? So this is actually 5.5. So now if you plot this profiles, let us say on the x axis you are plotting y plus, in fact you can use a log scale and plot this on the x axis, and on the y axis you can plot the logarithm of u plus. Okay. You should understand this y plus varies several orders of magnitude. Within the laminar sublayer, you are talking about the order of y plus is around 1, whereas in the turbulent boundary layer it can extend up to a y plus of close to 1000 at the edge of the turbulent boundary layer. So therefore 3 orders of magnitude we cannot plot on a linear scale. So we have to use a log scale to plot this, and similarly the variation of u plus also will be quite significant. So if you therefore plot this on a log scale, what do you have for what will happen to this profile? U plus is equal to y plus. So this is a linear, on a linear scale this will look like a straight line, but now on a log scale it will look something like this. Okay. So this could be, the edge of this will be somewhere around
is u plus is also on a logarithm scale?
U plus need not be on a logarithm scale. We can actually plot this directly on a linear scale itself, but the y plus will be on a logarithmic scale, because y plus variation is quite significant. For example, if if you start from 0, this will be 5, okay, and I am just plotting the actual y plus, how it looks. Okay, if suppose you plot it on a log scale directly, okay, and then you have somewhere here variation of about let us say 50, and then we have about 100 and maybe 500, some kind of variation like this. Okay. So, if you plot the linear profile, so this will be looking like a curve on the logarithm scale of the x axis, and then if you plot the log profile here, this is y plus is equal to ln of u plus is equal to ln of y plus. So, that will look like a straight line. Okay. So, but this limit will be a straight line from somewhere like this. Okay. So, the reason being, if you look at the extent of the laminar sublayer, it will be usually the order of 1 to 5, and this is not a sudden jump from the laminar sublayer into the fully turbulent boundary layer. So, there is a transition in between. When you do the experiments, okay, you find that it does not directly, this point directly does not transition to this. Okay. So, the fully turbulent boundary layer will actually start from y plus, which is greater than 30. Okay. So, you can actually look at the corresponding x axis, it will be around 30. So, there is a discontinuous region between the laminar sublayer and the fully turbulent boundary layer. So, in order to patch this, later on von Karman, student of Prandtl himself, he used a simple correlation, again empirical, not rigorously derived like the way we are doing this. So, he just made sure that there is a smooth transition from this region to this region. In fact, let me draw the slope. The slope will come out to be something like this in the log layer. So, this is your u plus is equal to y plus, this is your u plus is equal to 1 by 0.41 ln of y plus plus 5.5. Okay. Now, in order to patch this to this, von Karman introduced another intermediate layer, a buffer layer.
So now the x axis is y plus or ln y plus?
So, this is y plus, but I have plotted with a log scale. So, if you take a graph with a log scale on the y axis, on the x axis, okay. So, then you have a distribution of points like this. Okay, you have 0 to 10 and then suddenly 10 to maybe 100, then 100 to 1000. So, the order of magnitude will quickly increase. So, on this scale, since you are plotting directly ln of y plus on the x axis. So, this will be a linear curve, right. So, now the intermediate buffer layer is supposed to provide a transition from the edge of the laminar sublayer to the starting of the fully turbulent boundary layer. So, this was actually called the buffer layer derived by von Karman, and it uses a similar kind of logarithmic variation, but with different slopes. So, this turns out to be minus 5 times ln of y plus minus 3.05, and this is valid for a y plus greater than 5 and less than 30. Okay. So, this is valid, the pure log law is valid for y plus greater than 30, and the linear law is valid for y plus less than 5. Okay. So, this derivation is just to make sure that your u plus recovers at y plus equal to 5 the value of the laminar sublayer, and at y plus equal to 30 it should recover your original log value. Okay. So, it is just like a buffer between your turbulent boundary layer and your laminar sublayer. Of course, you cannot really visualize this or we cannot really see this in experiments, but this is how it is conceptualized. Okay. So, definitely the viscous sublayer exists, okay, but how the transition happens, it is all concepts. Okay. So, I mean this is what has been widely accepted, because it is reasonably a good a good patchwork rather than complicating it further. Okay. So, this is a classically accepted variation of velocity profile from the wall all the way to the fully developed fully turbulent boundary layer. Okay. So, and also this has to make sure you do not have any adverse pressure gradients. So, if you have adverse pressure, this is therefore derived for the case of a flat plate boundary layer. If what happens if you have a favorable or adverse pressure gradient, again those pressure gradients will change the nature of these profiles. Okay. So, then you have to do an experiment and then find out how these profiles vary and then plot them. Okay. So, this is the basic idea about the variation of velocity profiles. Now, one thing I just want to emphasize, from the Rance equations we can again write down the boundary layer equations for turbulent flow, because those Rance equations again are generic Navier-Stokes equation. You can apply that to any kind of flow with pressure gradient, without pressure gradient, with all kinds of diffusion in different directions. But if you want that to be solved specifically for say the flat plate boundary layer, okay, so we have to write this in a classical boundary layer form. So, can you try writing down the turbulent boundary layer equations from the Rance equation? We will use the same order of magnitude analysis that we did earlier for the turbulent boundary, for the laminar boundary layer. Same conclusions come out. The diffusion in certain direction is predominant over the other, the y momentum can be neglected, and these same facts can be used, and only we are applying this to our Rance equation. Okay. So, therefore, the continuity equation remains the same, except that you replace the instantaneous components with your mean components, and out of the two momentum equations, the dominant momentum equation will be in the x direction. Okay. So, this is your x and this is your y. So, therefore, we can write this as u bar du bar by dx. So, the advection terms will be as they are, and we can also include the pressure gradient term. And what about the diffusion term now? So, you remember that we have two diffusion terms, and we have also combined the turbulent stresses as a diffusion along with the molecular diffusion. So, we have diffusion in the x direction and in the y direction. So, according to the order of magnitude analysis, which is the dominant diffusion? In the y direction. So, we have to just retain d by dy of, so we have nu plus nu t into du by dy. Okay. Now, in the y momentum equation, y momentum itself is negligible compared to x momentum, and therefore, we have dp by dx is 0, there is no dp by dy is 0, there is no variation perpendicular to the plate length. So, you can use bars everywhere here. Sometimes it is understood implicitly that when you write this equation, they are all for mean flow. So, you can actually omit them, it becomes painful to use bar every time, right. And finally, the energy equation also for the turbulent boundary layer becomes alpha. Now, when we are using here, we have to be again careful, d by dy of alpha plus alpha t into dt bar by dy, right. So, we have the dominant diffusion, both momentum and thermal diffusion happening in the vertical direction, that is where the boundary layer is varying, you know. So, well, again, do you think that we can find analytical solutions to this, like the Blasius solution? It looks that we have simplified the Rand's equation for the boundary layer, but the major problem is mu t. It is not a thermophysical property, we cannot assume that to be a constant, and wherever Blasius has used nu, we cannot replace that with nu plus nu t. Okay. So, now this is where the problem comes. So, we cannot simply find similarity solutions for the turbulent boundary layer the same way that we have found it for the Blasius equation for laminar boundary layer flows. Okay. There have been some attempts to find kind of similarity solutions, but the kind of effort that we put into it is not worth it. So, it is better to go for approximate methods. Okay. So, usually the easiest route to finding the solution to these equations is to use integral equations, momentum integral equations, approximate methods by solving momentum and energy integral equations. So, we will have the same kind of equations that you had earlier, except that wherever we had nu, we will now have nu plus nu t. Okay. Now, how is it going to simplify? It is not going to simplify there, but the kind of profile that we are going to take for velocity, we cannot take a linear profile or for the matter quadratic or cubic. So, you are left with only one option, which is to assume what is called as a 1/7th power law variation. That is, in the case of flat plate, we assume u by u infinity as y by delta to the power 1/7. So, this is called the famous power law equation. It is a reasonably good assumption for a turbulent velocity profile. Okay. So, this 1/7th power law, however, has a difficulty, unlike your quadratic or linear profile. What is that? So, what happens to the derivative of velocity at the wall? You will have a singularity, correct? So, this is a problem. So, that is why you cannot use this profile to calculate the wall shear stress or the gradient of velocity at the wall, because you need that when you have the integrate this. On the right hand side, you will have nu plus nu t du by dy at y equal to 0, and du by dy at y equal to 0 you cannot determine from the 1/7th power law. So, then what do we do? So, we do not have any other option but to use some correlation for the wall shear stress. Okay. Although this is the best variation of velocity for turbulent boundary layer, we cannot use it to integrate right up to the wall. At the wall it becomes a singular solution. Therefore, we will have to use some kind of an empirical formulation for the wall shear stress, and usually the variation is used from the Cf is equal to 0.046 times so this is Re delta to the power minus 0.2. So, this is the kind of correlation that is the most commonly used for approximating the wall shear stress in turbulent boundary layer. Okay. So, this is nothing but tau wall by half rho infinity square. So, therefore, if you take the half on the right hand side, this becomes 0.023, and this Reynolds number is based on the boundary layer thickness. Okay. So, therefore, this will be u infinity delta by nu to the power minus 0.2. Okay. So, in the idea in the integral method then is to substitute this for the right hand side. Okay, at the right hand side we have this entire term is going to be tau wall, correct. Since we cannot use that profile, we will directly substitute for tau wall from this, and now we will have an equation which we can solve and find out the expression for boundary layer thickness delta. Okay. So, that is the same thing you do in your classical momentum integral equation, except that the right hand side you integrate the profile up to the wall, but in this case you cannot do that. So, we have to therefore patch it with a correlation on the right hand side, find out the expression for delta. So, delta as a function of Reynolds number. Okay. The same expression can also be used for internal flows. So, in internal flows you will be replacing your Cf with your friction factor, and this friction factor has to be which one, fanning or Darcy? Fanning, because tau wall by half rho u infinity square is the fanning friction factor. Darcy is defined based on pressure drop. Okay. So, the equivalent will be using the fanning friction factor once again, which will be tau wall by half rho infinity square, which is the same thing 0.046. Now, only difference is the Reynolds number will be now defined based on the diameter of the duct and not based on the boundary layer thickness. Now, this is for the fully developed turbulent boundary layer. So, there since your boundary layer thickness does not vary, so we will use the hydraulic diameter rather than the value of delta. Okay. So, these are the most famous relations that are used. If you look at in fact the Moody's chart for internal flows, the turbulent for the turbulent region, it is also plotted as a function of the roughness of the surface. So, that is a more detailed expression, because in turbulent boundary layer surface roughness also plays a very important role, and these correlations are basic, they do not account for surface roughness, right. So, therefore, the Moody's chart also expands this basic correlation to account for the effect of surface roughness, right. So, next, therefore, now that we know the wall shear stress in turbulent flows, turbulent boundary layer flows is obtained from this kind of an empirical correlation. Next is to go for the solution to heat transfer. Okay. So, how do we therefore get the solution to the heat transfer? Now, what do you think? I mean, if you talk about the approximate methods, you will use the momentum integral method, find out the expression for delta, and obviously then you want to go to the energy integral equation, find out an expression for the thermal boundary layer thickness. But will that give you the Nusselt number? Well, in a laminar boundary layer, okay, so your Prandtl number is governing the ratio of your molecular diffusion, ratio of the momentum and the energy diffusion. But what happens in a turbulent boundary layer? Okay. If you talk about this boundary layer, this is actually your turbulent boundary layer thickness. So, this is governed by the turbulent Prandtl number. Okay. So, therefore, now the question becomes, I mean, whether I can use the energy integral and integrate it up to delta t, and what is delta t here? Is it only within the laminar sublayer or within up to the edge of the turbulent boundary layer? So, that becomes a problem. So, therefore, what we will do is we do not actually solve the energy integral in this case, but we will try to find an analogy between the momentum and the energy transfer. We already saw in laminar boundary layer there is a clear analogy between the two. If you replace u by u infinity with theta, the structure of the profiles as well as the equations become identical, and especially if your Prandtl number equal to 1, they are exactly the same, right. Your du by dy at the wall and d theta by dy, both the skin friction coefficient and the slope of the temperature gradient, they are identical. So, what happens in the turbulent boundary layer, we will quickly use these kind of relations and derive the analogy for the turbulent boundary layer. So, the first analogy that is quite popularly used is called the Reynolds analogy. So, now we are talking about analogies between heat and momentum transfer. And the most popular is the most basic also, it is called the Reynolds analogy. Now, we have the picture of the turbulent boundary layer here, which has 3 layers in fact, okay, according to the hypothesis that we have a linear variation in the laminar sublayer, we have a buffer layer, and then we have a turbulent boundary layer. Okay. So, now we can actually look at all the 3 layers together, and that brings a very complicated picture. Okay. But to start with, we will assume the entire boundary layer is turbulent, there is no laminar sublayer, there is no buffer layer. So, this is called a one layer model, okay. And Reynolds analogy is derived based on this one layer model. So, only turbulent boundary layer extends all the way from the wall to the edge of the boundary layer, okay. So, in that case, let us again write down the expression for the shear stress from which we derived this law of the wall. So, this is your nu plus nu t into du by dy, okay, bar. And how about for the wall flux, heat flux? So, this is for the shear stress. Similarly, for the heat flux, we can actually use q double prime by rho Cp, and that should be equal to minus alpha plus alpha t into dt bar by dy. So, this is your extension to your basic Fourier's law of conduction. We also now include the effect of turbulent thermal diffusivity into this, right. So, therefore, if you just assume only one layer which is completely turbulent, so there will be no effect of the laminar or molecular diffusivities. So, only the turbulent diffusivities will be dominating throughout, okay. So, in that case we can therefore divide, let us call this as equation 1 and this is your equation 2, we can divide 1 over 2 and we will be therefore, so 1 divided by 2 you have tau Cp by q double prime equal to minus du bar by dt bar. If Prandtl number, turbulent Prandtl number equal to 1. Okay. So, I am just making an assumption that right now my turbulent Prandtl number equal to 1. So, that the ratio of turbulent momentum to turbulent thermal diffusivity is equal to 1, okay, and therefore, I get a very simple relationship between q and shear stress. So, this is how we are building the analogy. So, if you therefore integrate it, so for example, if you draw the velocity profile and temperature profile. So, this is some kind of let us say m mean velocity outside, this is T wall and this is T m at the edge of the boundary layer. Okay. This is the variation of temperature profile vertically and velocity profile. Therefore, if you integrate it at y equal to 0, your u is 0 and y equal to at the edge of the turbulent boundary layer, your u becomes um. Okay, I am using um because the um can be u infinity in the case of external boundary layers. Internal boundary layer, this is your mean velocity. Similarly, your temperature can vary from wall temperature to mean temperature. So, I will just integrate it and upon integration I can get, therefore, so if I integrate the shear stress, what happens? So, I have at the edge of the boundary layer the shear stress is 0, whereas at y equal to 0 it is tau wall. Okay. Therefore, I have tau wall Cp by, similarly the heat flux, right, this will become wall heat flux here. On this side I have um divided by T wall minus Tm. Okay, please check that you integrate it from the wall to the edge of the boundary layer, right. Okay. So, now I am going to introduce, I already introduced the definition of Stanton number to you, which is nothing but h by rho Cp um. This is nothing but Nusselt number by Re into Pr, correct. So, can you cast the equation, let us name this as equation number 3 here, the integrated one, in terms of Stanton number, okay, and therefore, tell me the relation between Stanton number and non-dimensionalize the shear stress, wall shear stress in terms of the friction factor, the fanning friction factor F. So, give out a relation between Stanton number and F, use this equation. Should be able to multiply it with some term, so that you can write this in terms of Stanton number. And H is nothing but q wall double prime by T wall minus Tm. Okay. By, for example, rho numerator and denominator. So, q wall by T wall minus Tm is h by rho Cp, I can multiply numerator and denominator by um, right. So, this will be h by, I take this rho Cp and um. So, that will be Stanton number, okay. And then I have tau wall by rho um square, that is nothing but f by 2, right. So, therefore, finally I get the relation in terms of Stanton number as f by 2. And what is this? This is your Reynolds analogy. Remember, you derived the same thing in laminar boundary layer. We derived it from the expressions for Nusselt number and skin friction coefficient that we got from exact solutions, and we got the same expression in laminar flows. Now, in turbulent flows also we are getting the same analogy, assuming that the entire boundary layer is turbulent and also your turbulent Prandtl number is 1. So, it is not hard to visualize it if your entire boundary layer is turbulent and both the diffusivities are same. So, once again, if you look at the nature of this equation, therefore, your velocity gradient and temperature gradient have to be having similar values, okay. So, therefore, the Reynolds analogy is also applicable for turbulent boundary layers. Now, if you use for internal flows, so in internal flows already we have the relation between f and the Reynolds number. So, please substitute this, okay. Now, one more thing. So, this is your Reynolds analogy. Later on it has also been extended to various Prandtl numbers. So, it is for the case where Prandtl numbers not equal to 1, it has been extended and this become the Reynolds Colburn analogy, where you have Prandtl number factor also. So, this is your Reynolds Colburn analogy. Okay. So, the effect of the molecular Prandtl number is also brought in into this. Okay. This is not turbulent Prandtl number, this is molecular Prandtl number. Okay. The effect of molecular Prandtl number, which we have neglected here, has also been brought in later by Colburn and extended to different values of molecular Prandtl number, because at the wall finally molecular Prandtl number is important. We cannot claim that we can predict the Nusselt number, okay. Nusselt number is a quantity at the wall without accounting for the laminar diffusion. So, therefore, later on Colburn adjusted this for values of molecular Prandtl number. So, now you can therefore substitute the expression of f into this and get the expression for Nusselt number as a function of Reynolds number and Prandtl number. Can you do that? You already have the Reynolds number dependence here, okay. So, what will be this constant? 0.0, I am just substituting directly for f, 0.023, I have RED power 0.2, but Stanton number is Nusselt number by REPR. So, I have 0.2, this is minus 0.2 into 0.8. So, you will have into Reynolds number. So, it will be RE power 0.8, right. And what about Prandtl number power? So, this is again REPR, okay. So, 2 by 3 minus 1 by 3. So, 1 by 3 and then this is therefore 0.3, okay. This is therefore a correlation for Nusselt number directly derived from the analogy. So, we are not solving your energy integral or anything here. Okay. So, this correlation directly gives you a very simple approach directly from the analogy. You know the expression for the wall shear stress, therefore, we use the analogy and directly get the expression for Nusselt number. This correlation is popularly referred to as Dietz-Boelter equation. It's a very fundamental equation that many people know in heat transfer, turbulent heat transfer in ducts, flow through ducts, no fully developed turbulent flow through ducts, but you may not know how it is derived. You have used this as a correlation without knowing how it is derived. It is nothing but derived from a simple application of Reynolds-Colburn analogy. Okay. It is not very rigorous, but it has been found to be a reasonably good approximation within plus or minus 20% to the experiments. So, when people do experiments on fully developed turbulent pipe flow, they compare it with the Dietz-Boelter and find that it is very close. So, now how do we deal with the external flows? So, this is for the internal flow, you have the Dietz-Boelter. Now, in external flow, your Reynolds number here is defined based on boundary layer thickness. Then what do we do? So, we use the momentum integral, get the expression for boundary layer thickness as a function of your local Reynolds number, and that is put into this, substituted into the Reynolds-Colburn, and you will get a similar expression for the external flow also. Okay. So, only thing there you have local Reynolds number. In fact, the variation is similar, same. You have, instead of RED, you will have REX power 0.8, Prandtl number to the power 0.3. This constant will be slightly different. It comes out to be something like 0.029 in external flows, because you are substituting delta from the momentum integral. So, the constant will be little different, but the dependence on Reynolds and Prandtl number will be the same. Okay. So, for the internal flow case, it is a very straightforward thing, whereas for the external flow you have to use the momentum integral, solve it, then use the Reynolds-Colburn analogy. Okay. So, therefore, although the turbulent flows are considered theoretically very complex, so very reasonable simplifications like these have yielded useful results. Okay. So, sometimes it looks that they are oversimplification, but when you do experiments, measurements and compare, so these correlations agree very well, and therefore they have been well accepted even in industries. Okay. So, this is one simple analogy, but most often used. There are analogies which are taking into account multiple layers. So, from one layer we can therefore transition to two layer, accounting for the viscous sublayer and the turbulent boundary layer. So, that is called the Prandtl analogy, Prandtl-Taylor analogy. And finally, we can also include all the three layers, including the buffer layer. So, that is called as the von Karman analogy. So, we will derive these two analogies. At least I want to derive the Prandtl analogy, Prandtl-Taylor analogy, or the two layer analogy, then I will just give you the expression for the three layer analogy. So, most of the turbulent heat transfer is dealt with using these analogies. Okay. So, if you go for complex flows where you have flow separation or very strong pressure gradients, then these analogies will not work. Okay. So, in that case you have to solve the Rance equations and again model the turbulent viscosity, whether you use a one equation model, two equation model. So, those depending on the level of complexity and the computational time, you can therefore solve them more rigorously. Okay. But for simple boundary layer kind of problems, these analogies are the most commonly used. Okay, so we will stop here, and following Tuesday, Monday they do not have a time in the studio. We will meet on Tuesday at our regular time 10 o'clock. That is the last class. So, we will complete the other analogy also, okay, and with that we will complete our turbulent boundary layer convective heat transfer. So, any other questions or discussion, if you have time, I think for 10-15 minutes we can do that.
Monday is Friday.
Monday is following Friday timetable, is it?
Yeah.
Okay.